So welcome to this new meetup for May 2022. My name is Didier. Together from the HP developer community team, I have Mathieu with me. Mathieu will be cutting, pasting links into the chat while I'm doing the introduction. Before I hand over to Evan, our speaker today, I just want to do a couple of housekeeping items for you about the HP developer community. Today, the topic from Evan is about scaling language training to trillion parameter models on a GPU cluster. But before we get to that, let me remind you that this is part of a program that we call Meetups. This is a monthly series that we started this year. We try to have open source topics there. We have already signed up somebody from AWS to talk about OpenSearch in June. And we have somebody from DeepFence talking about Threat Mapper in July. So this is the calendar that you can find, where you can find all those links to register to our meetups. This is externally available. Don't hesitate to invite anybody you'd like that you think might be interested. In this page, you'll find also the replay link for all these sessions. Once we have the video available on our YouTube channel, we'll update the calendar page to reflect that, and you can see that in the replays. This complements another series of talk we call Munch and Learn, and this we started last year. We are running those. They're a little bit different in target audience, I would say. These are more like trends, thought leadership, kind of vendor agnostic, and product agnostic. So we have no session in June because of our HP Discover calendar, and our next session will be in July, but I don't have a topic completely confirmed yet. So I will update the calendar as soon as we can. So it's a different page, and there again you can find the registration links for the upcoming sessions, and you can find also the replays from the past session starting last year. Couple of additional things you want to know about the developer community. We have a number of other things that might be of interest for you. More specifically, we have a thing we call workshops on demand, and these are Jupyter Notebook-based workshops that we deliver through the Hack Shack, we call it. So you can get to that URL here and find the list of our 27 workshops that we have available. This is available for free, 24/7. Again, it's open to external audiences. So take a look. We have about 19 open source topics there, from programming Python to programming Rust to what's a REST API, a 101 on Docker, Spark, Kubernetes, and many others. So give it a try, provide feedback of what you liked, what you didn't like. Again, this is a community that we are dealing with here, so we need amplification and contribution. So please join and invite others to this type of talks if you think they would be interested in. We have a monthly newsletter which you can subscribe to. This is the link, and I'm sure Mathieu is pasting links in the chat right now. Feel free to join that newsletter to keep up with what we do. There's a button at the bottom of that newsletter to unsubscribe if you have a problem with that. You can invite others to join our discussion on a dedicated Slack that we have here. You get yourself invited from that URL here. We have a Twitter account with a huge crowd already following us. And if you're interested in contributing more in that sense, like write a blog, for example, we would be really happy about that. And you can check that page where we show you how to do that. We use a content management system for our website that is based on GitHub and Markdown. So it's pretty straightforward for developer alike to contribute blogs. You can also deliver a meetup if you're a subject matter expert in a particular topic. Just reach out to us. And you can also propose and help build workshops on demand if you're a subject matter expert that would like to go even deeper on something. So that's kind of, in a nutshell, how you can join the community. Thank you very much. Our main website is hpdev.io or developer.hp.com. You can scan that code to get to our community page. And with that, I would like to hand it over to Evan for the rest of the session. Thank you very much.
Awesome. Thanks for that introduction, Didier. Really excited to be here, part of this community, speaking with you today. And before I get into it, I just want to, call out that everything I'm about to share with you today is actually open source and accomplishable with open source technologies. So I'll be talking a little bit about some of our commercial offerings here at HPE, but particularly towards the end of the talk, I'm going to show a live demo that's going to be, something that you could go out and recreate yourself with open source, which I think is really cool part of the world that we live in 2022. So just as an introduction, I'm Evan Sparks. I'm Vice President of AI in the high performance computing business unit here at HPE. I came over to HPE last year as the result of the acquisition of my company, Determined AI, where we built an open source training platform for large scale deep learning, which will feature prominently here in kind of the discussion today. So today I'm going to talk about something pretty ambitious, which is scaling the training of these large-scale language models to potentially 1 trillion parameters using a GPU cluster, and kind of talk about the journey that we see customers having to take to get there. And if you don't know what a large-scale language model is, don't worry, we'll talk about that in a little bit during the introduction. But suffice it to say, this is a very it's a very interesting area of computer science right now, where we're seeing large-scale deep learning and language models that are bigger than anybody could have imagined just a few years ago, really delivering outstanding performance on a variety of natural language processing tasks. And we'll talk about those in a little bit as well. And it's driving both, really incredible applications, but also, it comes at a substantial cost, and you really want to be thoughtful about how you scale these things. And so we'll talk through kind of what that journey is for customers and users in a moment. And at the end, I had planned to give a live demo, but unfortunately the demo gods are cursing me today. So I'll show you a pre-recorded version of that demo. So apologies. I just want to make sure that there's nobody feels like there's a bunch of smoke and mirrors here. All right, so let's talk a little bit about these large-scale language models, and then we're gonna talk about the challenges associated with scaling them, and then as a developer, as a machine learning engineer, what are some best practices that we see our customers and users kind of following as they're pushing these models to scale? The old expression, Rome wasn't built in a day. I think that applies to these large scale language models as well, as you'll see in a moment. So what do I mean when I say large scale language models? So without going into too much technical detail about transformers and so on, what I'll say about these language models is that they are an amazing statistical artifact that is coming out of academic research from some of the top labs in the world. Both industrial folks like Google and so on are pushing the envelope in these language models, as well as in academia. Friends at Stanford have created an entire research center devoted to these so-called foundation models. And what they are you can think of it, very crudely, as you ingest a whole bunch of data as input to these language models, and it can be unlabeled text, usually, like, I don't know, all the English language text on the internet might be something that you try and feed into one of these language models. And then through a training process, you end up with a statistical object that is counted in terms of the number of parameters that forms an encoding of that data that can then be used for lots of other downstream tasks. And they have these large transformer models, as they're called, have shown to beat state of the art on a wide variety of tasks in natural language processing. So basic stuff like entity and event extraction, things like document summarization. You take a long legal document and you want to get the essence of it in 2 paragraphs, to things that are, you wouldn't think of as natural language at all, like programming languages. And I know I'm at a dev talk, so I'll talk a little bit about these. If you've used GitHub Copilot, which is a plugin for VS Code, where you start typing code and it auto completes, not just like the next variable in your function call, but sometimes entire method bodies or entire class structures are kind of pop out for you. And it won't be exactly what you would find on the internet. It'll be some interpolation of the code that you've already written in your file, plus the, as a prompt for this language model, and what it knows from, say, pulling data from GitHub. DeepMind has a system called AlphaCode, which has been shown to beat the average human participant in competitive programming competitions. Now, average competitor is only so, doesn't get anywhere near the people who are sort of at the top of the leaderboard of these competitions. But in a couple of years' time, and maybe with more training data, it'll get there. The list goes on. So there's document summarization, there's machine translation, semantic search. All of these things can be enhanced through the use of these large language models. And probably the most popular one, or the one that most people have heard of, because there were some pretty amazing demos flying around the internet last year, is a model called GPT-3. So GPT-3 was, we'll show you how big it was in a minute, but it comes from the folks at OpenAI. So this chart gives you a little bit of the sort of what's the catch and the progression of these things. So in ancient history in 2018, so not that long ago, there was one of the first of these transformer models called Elmo came out, and it was about 100 million parameters, 100 million. What we have seen is that as we enlarge these models and we put more data at them, they just seem to get better. And it's not clear what the limit is in terms of how much better is better here. And so importantly on this graph, this is on the x-axis is time, so years, 2018 through basically today. And then on the y-axis is the size of these models in terms of billions of parameters. So note that this is a log scale. So these models have gotten 1, 2, 3, 4, 5 orders of magnitude bigger, I should say, in terms of number of parameters. And with that has come extreme computational complexity to actually train these models. So you can see it on the slide. Training this GPT-3 model up here, one time, start to finish, costs about $3 million on the public cloud. And that estimate is based on publicly available public cloud costs, a month of 1,000 A100 GPUs on AWS is about how long you're looking to train one of these models. I think AWS has a recent blog post that says they've been able to get this down to about 21 days or something like that. So progress, but it's still very directionally quite correct. And then meanwhile, you also start to think about the environmental concerns. And I gave a talk with my collaborator, Amit Talwalkar, a little while ago about just this very, impact of gosh, how much energy are we talking about when we're training these large language models? And, some estimates that come from folks at Google and Berkeley say that this is going to take about 1.2 or 1,200 megawatt hours to train one of these models once. And that is, again, start to finish train one of these models. Now, these models are used for downstream tasks. So, there's some debate about, okay, how is that, that amount of money or that amount of energy amortized to these kind of downstream tasks. Usually you take these models and then you fine tune them on your particular task, but somebody has to train them once in the first place. And then also, there's a big variable, which is what is the training data that the model was originally trained on. If I'm looking only at English text on the internet or code on GitHub, that might not be relevant at all to my downstream language task. If I'm studying, say, alternative languages that aren't English or I have proprietary data that's highly specific to my customer environment that I want to build one of these language models off of. So all of those things are kind of reasons why you might want to train one of these things from scratch. Now, there's some really great work that came out of Stanford and NVIDIA and Microsoft Research about a year ago, a little less, I guess, by Deepak Narayan and a whole bunch of collaborators. And this was called the Megatron LM paper, and it was about how do we get a large-scale language model to train on a big GPU cluster. And that's the subject of this talk as well. And so I want to point out that in many ways we are absolutely standing on the shoulders of giants here with the work we're doing here at HPE. So in this paper and corresponding kind of blog post associated with this paper, Deepak and his collaborators do a great job of kind of outlining some of the challenges to scaling training these models. So if you go from using a single GPU to train your model to using 1,000 or more, what are the challenges you run into? And the biggest challenge is how to parallelize that training process and what the right way to parallelize that training process and really drive sort of optimal throughput of that training process. Because if you're going to use 1,000 GPUs for any length of time, you kind of want to make sure you're using them the right way. And so they outline a number of optimizations around this parallelism, and everything from and they kind of introduced this concept of the 3Ds of parallelism: data and pipeline and tensor parallelism. So data parallelism means I shard my training data, and each node in my cluster sees a piece of it and uses that to train, and then the nodes exchange kind of their model weights through a communication efficient process. But these models are sometimes too big to fit on even one node's worth of GPUs. So if I've got a trillion parameter model, that might not fit easily in memory on my GPUs. And so what happens is you start doing tensor parallelism, which is to shard the model across these nodes. And so one model might need to fit on 4 nodes out of your 200 node cluster. One instance of the model, and then the same kind of communication that I alluded to earlier happens. And then the third P of parallelism is what's called pipeline parallelism, which is to say, maybe the training process happens where one set of nodes is responsible for the first part of the pipeline, the second set of nodes is responsible for the next set, and they pass data backwards and forwards through the training process between one another. And that's a little bit of a technical concept, and if that doesn't make sense to you, don't worry about it. It's another lever that we have in terms of how to parallelize these things. And then the question becomes, what is the right way to balance these various degrees of parallelism? Do I want to, start with as data parallel as possible, and then only then introduce model parallelism when I have to, or whatever? And they offer some guidance here, but I'm going to show you how we kind of take that idea of balancing these parameters to the next level and actually automate it. So, that's all great. There's a great, there's a paper out there, there's open source code on GitHub, but our customers don't usually care about just replicating the benchmark and rebuilding what has already been built in the open source by some of these various research groups. What they care about is innovating, and they care about maybe training a model that's more appropriate for them on their data, with their maybe modifications of the model. Maybe they have some idea about how they want to incorporate not just text but images into one of these transformer models, or they again want to train on different types of language data than were anticipated in the original design. Maybe they want to customize the model architecture itself. All of that is stuff that should be fair rein if you're pushing the envelope and innovating. So then I have a little poll here that we might want to run, which is, in the audience, if you've trained a deep learning model, it doesn't have to be a language model or whatever, but have you ever actually trained a deep learning model and had it work the very first time? So first question is, have you trained a deep learning model at all? And so I see, it's not quite 50-50, but we've got a good chunk of the audience, maybe about a third of you, something like that, who have actually trained a machine learning model before. So that's the first question. And then the second question, and I'm not sure if we've got this, but the next question is really how many people have had that actually work the first time? And I don't mean like I clone a well-known repo on GitHub and hit train. What I mean is you start modifying it for your problem and your data, and you just get to convergence very quickly. So I see, I think this is actually a rigged question, because I've been doing this a long time myself, and I have never, ever seen a model that just worked out of the box. You always, there's some issue with the way your data is formatted, or gosh, because the data set is different, the learning rate is off, or whatever. Like there are many different variables and ways that the training of deep learning models can go wrong. That's okay. It's a highly experimental sort of process in today's world, that that means, though, that if training one of these models costs $3 million, I'm going to make a lot of mistakes before I get to the one that actually works. And I don't know about you all, but my boss doesn't let me kick off $3 million jobs willy-nilly. I kind of have to plan for that sort of thing before I get going. So okay. So even with that kind of warning, maybe you still want to train one of these large scale language models because you think you've got an idea that's going to revolutionize your industry or whatever. Now, the question then is, why is training one of these large scale language models harder than cloning that GitHub repo that I just mentioned earlier and running it? So I wanted to walk you through kind of some of these practical challenges in really doing any kind of large scale deep learning today. So, first is sort of, I think that the world has improved to the point in the last, say, 5 years where actually getting started and doing what we call day one of deep learning has gotten really, really easy. When I was in grad school, you were, emailing other academics for their code for their particular thing. Everybody was writing in different frameworks. It was all like very hand rolled. In the last few years, thanks to frameworks like PyTorch and TensorFlow, and thanks to all the great work that's been going on at NVIDIA and some of these other accelerator vendors, getting started with deep learning is actually dramatically easier than it used to be. I can pip install one of these libraries. I can go read a tutorial on the internet and clone the right repo, and I can get started on one machine on a single GPU really quite easily. It's fantastic, actually. And so as an individual researcher, I can actually start to think and try new things out and whatever. Where we see a lot of the practical challenges come in with deep learning is as you move to scale. Companies like Google and Facebook and so on, they have amazing infrastructure designed to let their teams of machine learning engineers and researchers leverage maybe lots of different frameworks at a time on top of lots of diverse hardware simultaneously. And that kind of tool set that allows people to share their GPUs, allows people to automate their workflows through things like hyperparameter optimization and neural architecture search, that allows them to share the results of their experimentation and so on, as well as to share effectively and scale up the use of the GPUs or other accelerators that they have in their clusters. Those tools aren't available outside of those big companies. They're not really available to the rest of us without a real push from the community. And you can kind of see where this is going. But the point here is that this challenge of scale and scaling up training of deep learning models is really hard, and it takes a lot of work for especially for domain experts and scientists and machine learning engineers who are really focused on on the data and the model that they're training, and maybe aren't experts in this kind of underlying systems and infrastructure, and maybe they shouldn't need to be. And so at HPE and previously at Determined AI, my company that I mentioned, we built and continue to build an open source platform, software platform for large scale deep learning that is designed to address many of these challenges. And it's designed to help give those machine learning engineers infrastructure like they might have at one of those big tech companies, no matter where they are, whether they're running in the cloud, whether they're running on premise, whether they're at a small startup in the middle of nowhere, or just working in an academic research lab, or operating at a really big scale, like many of our customers do. And the HPE machine learning development environment is the commercial version of this software package, but the Determined training platform, as I mentioned, is the open source version of this. The big differences between the commercial and the open source are support and some enterprise features around security, as well as some additional kind of items that are on our roadmap. But again, everything I'm going to talk about today is accomplishable with the open source technology. And so that open source platform really consists of a number of different facilities designed to help machine learning engineers and users leverage effectively their whole clusters, collaborate with one another easily, automate their workflows, and so on. Now, as important as what this platform does is what it doesn't do. We don't provide facilities for data preparation and ETL and getting your data ready for the model training. We find that our users and customers have their own answers to those sorts of problems. We also don't do anything to help you with sort of serving your model. We might help you run batch inference in the product, but if you're running a real-time service that's rendering predictions from one of these models on a self-driving car or in a web service somewhere, there's going to be a downstream tool set that you use. And we're fully aware that we're part of this broader ecosystem of tools, and we work really hard to integrate with the broader sets of tools. So that's the platform that we're going to use to help make it simpler for end users to achieve the sort of scale that we're talking about. And so we're bringing some of these tools like DeepSpeed that I mentioned earlier in a form factor that's consumable and easily usable by end users, and taking care of that underlying, how do we efficiently allocate the resources? How do we scale the training and do that in a high performance way? So, I won't talk too much to this slide about some of the core benefits of the development environment. Again, encourage people here to check out the open source. We're really designed for scale and designed to help teams of engineers rather than being completely focused on individual developers, although you can install the system on your laptop and get going just as well there, as well as on a supercomputer. So now we get to the part of the talk where we're going to talk about, okay, what is some practical advice on how you train these large scale language models? And the answer is you train them very, very carefully. So the kind of joke I had earlier about my boss not letting me run $3 million jobs, that wasn't really a joke. It's really important to kind of start small and scale up. And so I'm going to paint a picture of sort of the best practices of scaling up really any large workload. This isn't actually specific to deep learning models. It's sort of as you go from a job that runs on maybe one computer, one thread, and scale it up. What are the good checkpoints along the way? And I'll do this in a way that I'll talk about this in a way that's grounded in these large scale language models. But again, I think it's an important general principle to follow. And so the first thing you do is you plan ahead for scale, and you think about, what is the scale that I actually need? How many GPUs, how many computers do I need to solve my big problem? And then kind of work backwards from there. Second thing you do is you never ever start by saying, okay, I've got terabytes of text from the internet, and I've got a target model, and I'm gonna just start right away. You don't scale, you subsample, you work on samples of your data as you're working to get things right, and you work on a smaller model that maybe has lower capacity so that you can iterate quickly and figure out, where did I make a mistake in my data loader code, or where did I, where am I making some mistake in a statistical transformation that's going to lead to poor performance. And so then, once you have downsampled, then we gradually encourage people to scale up. So, they go from maybe using 1% of the data to 10% of the data to 50% of the data, and so on. And then finally, we encourage people to tune for throughput. So I'll talk through each of these kind of steps in a little bit more depth here, and then I'll show you kind of how it works in a demo environment. I'm going to pause for a second and just answer a couple of questions that came in through the Q&A. So the first question comes from Luis, who asks, from a cybersecurity point of view, what's my perspective on how sensitive the training data set utilized for models like GitHub Copilot could expose private code to, in this case, GitHub Company? Yeah, it's a little bit Wild West. And so GitHub did train all of their, the GitHub Copilot on all of the publicly available code on GitHub. So they were careful to not train on private code. But people have shown actually that you're able to query the large language model from Copilot in certain ways to actually reproduce exactly some open source code that exists on GitHub. And so that's not necessarily bad from a cybersecurity point of view per se, because it was publicly available code anyway. But some of that code is actually GPL code, for example. And so, there's an argument, well, maybe this entire model has to be GPL because it touched GPL code, or it has GPL code embedded in it in some way. And it's kind of an ethical debate at this point. But you do have to be really careful when you're training these models that there are security attacks on them that can extract data from them and so on. And so, I'm not trying to frighten anybody or anything like that. There are really good reasons to use these models. But if I were to deploy one of these models in a production setting that where it was really on proprietary data, I'd probably have pretty strong admission control in terms of the types of queries I would allow end users to probe the model for. I wouldn't just kind of put it out there if it was trained on sensitive data. It's a really great question. So the next question is from Miguel Cruz. How much more complex will the handling of data drift in such large and complex models become? I think the answer to that question is that it's a little bit domain specific. And so usually when we're talking about these large language models, we're looking at them in a self-supervised kind of context. And so the data is unlabeled, and therefore, people kind of put really broad representative data into them. It's more about getting more data than really systematically the same data, as is the case in many other types of models. But if you were to fine tune and downstream one of these models on, or try and use one of these models on a modality of data that it had never seen before. So let's take the GitHub example. Let's say I trained my model just on English text and didn't have any code at all in my training data. The use of GitHub Copilot would probably not work at all in that set. You have to make sure that the query set that you're working on is somehow available in the training data. And so data drift can certainly become a complicating. That's sort of the most extreme version of data drift that I can think of off the top of my head. But again, a good question. It's a little hard to quantify in these settings. All right, so let's get back
before you move on.
Yep.
There's a couple of questions that end up in the chat.
Okay,
from
great.
Alessandro. I don't know if you have that window open or.
All right, Alessandro. So how does the HPE machine
Yes.
learning dev environment handle multi-tenancy? Say a customer is a service provider who wants to deliver AI training as a service to multiple different users. It's capable of partitioning of sorts between users in their training. Very good, very practical question on how we deploy this live. So usually the way we recommend it depends a little bit on the environment, but the simplest way to deploy that would be on a per customer basis or per group per consumer basis to deploy a separate copy of the determined AI or the machine learning development environment software. We can deploy on top of Kubernetes, and so you can have multiple versions of of the system running on the same cluster managed by Kubernetes at a time, or you could partition your system in that way. I wouldn't recommend putting two competitors in one instance of the system, even with some of the features we have coming out around role-based access control and so on. It's just not designed to it's designed more of a tool for collaboration and less in that kind of true multi-tenancy sort of environment.
One last question from Gavin at the bottom of your list.
Yep. Does it offer features such as fractions GPU and smart job queuing? So we, in terms of fractional GPU utilization, we support MIG, multi-instance GPUs from NVIDIA. And so you could have a cluster that has, if it's got one physical A100, it could have, I forget what the right number is, but maybe 4 or something, MIG GPUs exposed to as use. So you can fractionalize GPUs in that way. And then the other question is, does it support smart jobs queuing? Yes, we have a number of different scheduling. We have a couple of different scheduling backends. One is a weighted fair share scheduler, which is one way of, it's not exactly a queue, but it is a way of intelligently sharing the resources in a time division way across the cluster. We also have a priority-based scheduler with preemption, and so that's the sort of the smart job queuing, where we users can submit jobs while other jobs are running, and if they're higher priority, we'll preempt the old ones and pause them and restart them and so on. And we're able to do that pausing and restart because we understand the semantics of, or the system understands the semantics of the deep learning jobs and what is the checkpoint, how do we restore state and so on, which is harder to do with general purpose kind of computation. So great question. All right, so back to scaling. And I want to be kind of cognizant of time because there's about a 10-minute demo that we'll show in just a few minutes as well. So first thing you do is you plan ahead for scale. And so let's say I want to train a 1 trillion parameter model. We estimate that if we wanted to train such a model in about 3 months, we would need approximately 3,000 GPUs for 3 months. And that's basically back of the envelope based on what it takes to train a 175 billion parameter model, which I showed you earlier, and also based on some some testing we've done as well. And what's important here is not just the GPUs. I keep talking about GPUs and accelerators and compute. But actually, as you get to this sort of large-scale distributed training, it really makes sense to have a high-performance interconnect between these among these nodes. And so we recommend InfiniBand. A question becomes exactly how much InfiniBand we might need, and some of this is based on properties of the workload. And so if you're investing in sort of hardware here, it makes sense to think about, how do I provision, what's the right balance between my compute and my networking to sort of get maximal throughput. And we via our professional services we can help customers figure out exactly this, what is that balance. And so we've done this in the past where we say, okay, you know, assuming this type of networking topology and this type of model with this many parameters and this communication pattern, we expect that the rate level is maybe not 4 InfiniBand interfaces, but might be 2 or even less. And but the point is, you do need high bandwidth, low latency interconnects to drive these things forward. It's just, the question is just how much. And then from a software perspective, again, for this type of workload, we think you can get away with the machine learning development environment, which has bundled into it technologies like deep speed and a few others that we rely on, as well as if you're running on NVIDIA GPUs, you'll need cuDNN and Nickel, as well as an optimized version of PyTorch to kind of get going. Again, we actually make it really easy to, our default containers will ship with PyTorch and cuDNN and Nickel pre-configured. So all of that conceptually also ships with the determined AI or the machine learning development environment. So, that's the planning bit. So I'm going to use software that and hardware that is designed for scale. Then, the question becomes, what's the right way to downsample? And you'll see this in the demo in a moment, but we think it's important to both downsample not just the size of the model, but also the size of the data set accordingly. And what you want to do is get to a point where you can iterate rapidly on maybe a single node in your cluster. So if you've got a trillion parameter model on 384 nodes, so 3,000 GPUs fits on 384 nodes. Usually it's 8 per node, and in these high density kind of environments like the Apollo 6500. You might want to shrink that down to, say, a 26 billion parameter model, and that'll be, medium, even though just a couple of years ago that was considered absurdly large. Then you're going to scale down your data set size accordingly. So if you have 10 terabytes of input to start, you probably divide that by about 3,000, and that becomes the kind of test set you start to work with. So then the next thing you do is you've got your tiny or your medium kind of job lined up, and you want to run a bunch of these small jobs to really work and test your code paths and make sure your model is kind of behaving according to your plan before you get to training the large model. And what this chart below is designed to show you is, let's say, your big job, the trillion parameter model in this case, it takes 1,000 units of time to train. If you add in a bunch of overhead from running a lot of small jobs, the total overhead you introduce to your end-to-end process to prevent yourself from having to run multiple of these really large full jobs is actually quite minimal if you do this right, and you start with 1/3000th of the data set, and you kind of scale carefully between start to finish. And so that overhead, while you're developing, it can be, you really are itching to run the big model, but it's just really important to try and get it right at the smaller scale before you scale up. I'll answer a couple more questions before we get into sort of showing you what this looks like in terms of demo. I wanted to show one last thing, and that is the last thing you want to do is tune for throughput. So important to get it working, get it correct first, and then you optimize for speed. So you might run a handful of steps, so partially train a model on and make sure it works at scale. And I'll answer the question about scale in a moment. But then you really want to tune for speed and optimize, and we'll show you kind of how we have some automatic tools to do that in a moment. So one of the attendees asks, could you define scale, because it means different things to different people? What one person thinks is large scale might be small scale to someone else. Absolutely, it depends. And when I'm talking about scale here, usually I'm looking at it in kind of three dimensions: scale in terms of the amount of compute required or the amount of data. And here we're talking about thousands of GPUs over the course of months, which is, from a dollars perspective, we already kind of talked about what that might look like on the public cloud, millions of dollars, say, for a single job. And we're talking about footprints on really large, for months at a time, on what would be easily top 100 kind of supercomputers in terms of the scale there. So that, I don't know, it's maybe not scale to folks at Google, but it's scale to just about everybody else in the world. But that's only one dimension of scale. Other dimensions of scale might be the number of users you have working on such problems. We typically don't see, 100,000 users in one site working on these types of problems. Usually it's tens of users. They're working on very big jobs, but that's kind of the scale in terms of people. So those are kind of the important dimensions that I think about. And then there's scale in terms of number of jobs and concurrent jobs and so on.
Hey, Evan, sorry to interrupt. Yep. We have reminders note on top of your presentation. I don't know if you see it. But...
I see. Got it. Sorry about that. Great. Great. And so then the other another question. At Aruba Customer Success, we have a small data science team developing some ML models, not near as large as the ones you're talking about today. However, we'd like to use transfer learning to use parameters from known transformer models. Do you have some NLP models you could use as a reference for our exercise? Yeah, absolutely. So within kind of our example repositories, we show how to do just that. We also have support for a very popular open source library called Hugging Face, where we've made it really easy to run Hugging Face models and track your experiments and so on. It might be a small scale for starters, but as you grow your data sets and your use cases, you might hit scale faster than you think. So that's a popular feature, and I encourage folks to check it out. So it's called our Model Hub, and Hugging Face is the name of the library, and we can link to an example a little later. So another anonymous attendee said containers incur overhead, especially on I/O, quite noticeable with PyTorch configured to use MPI. Are you only providing the software to customers as pre-configured containers? The answer is yes, but we are taking advantage of, many customers take advantage of optimized containers from places like NGC that are designed to have, as high performance access as you might get in one of these containers. Generally speaking, the data access patterns that we see are quite bulky. They're not so much like lots of little low latency messages. They tend to be big messages that are transferred big chunks of data at a time, which tends to minimize some of these overheads for sure. Yeah, then the last question is, how have you got a comparison using your InfiniBand connected cluster with Slingshot on Cray EX? Dying to get some time on the Cray EX hardware and Slingshot. We are working on a version of the software that is designed specifically for HPC, and so that is running on top of HPC container technologies like Singularity for starters, but others going forward, as well as on top of existing HPC schedulers like Slurm. So working in that environment, we have our first customers deploying that kind of software in testing right now, but there'll be an announcement about that soon. The actual, Slingshot hardware and tuning, that's going to come a little bit later in the year, as we, as the hardware kind of becomes available more for internal testing. Really excited about Slingshot because of a lot of its properties around kind of the traffic shaping and so on, particularly in these multi-user kind of environments, making sure that the right jobs get the right type of networking for them, particularly in these mixed use kind of clusters, where some of what the cluster is doing is traditional HPC simulations and so on, but some of what it's doing is training large scale deep learning models, where those workloads are going to have slightly different properties, but being able to sort of share resources well in those environments is definitely an interesting challenge for us to go solve. Great. So just in the interest of time, I want to switch gears and show you a live demo of that tuning process that I just, or not a live demo, pre-recorded demo of that tuning process that I just mentioned. Using the Cray AI development environment, Determined AI, users bring in their model and they define a class that exposes their model to the system, and it's going to export their model using kind of standard APIs and libraries from PyTorch, and set up optimization and so on. Importantly, one of the things that we recommend that users do is to parameterize their models in terms of the model size as just that, as parameters, as configuration, rather than hard coding, the size and shape of a model. This is a code base based on GPT-NeoX that we've used to simulate this, and we're going from really large models to smaller models here. And what you see on the left is a GPT-3 size model, 175 billion parameters. Again, not what we're starting with, and what we're showing on the right is how we shrink that model down in order to be something that's closer to a few hundred million or a couple billion parameters that might actually run in reasonable amount of time. So you parameterize the size and shape of these models in configuration. Then once you have your code set up, using Determined, we make it, again, really easy to say, I want to run this model not on just one GPU, but on, say, 16 GPUs. And this is, again, just configuration. The user isn't making any code changes in order to see this. And it's taking advantage of a fast parallel optimizer in the backend, in this case, based on DeepSpeed and Zero from Microsoft. And that particular optimizer has some additional parameters that we'll get to in a minute, around the 3Ds of parallelism I mentioned earlier: data parallelism, pipeline parallelism, and model parallelism. But this is really kind of the fundamental ingredients you need to submit a job to the Determined system. And so Determined and the Cray AI development environment is a system that is designed to help you track and understand the types of experiments that you're running. You can see, clearly here we've got a cluster. It has happens to be on the cloud. It's running 32 GPUs, in this case NVIDIA V100s, but just for the purposes of this demo environment. We can see, history of models that have run in the past. We can understand what's going on in our job queue and see what's being scheduled and what's running right now. It's a fairly lightly loaded cluster. I'm the only user, and we can drill through and see things like the model registry, which contains output, some of that tag sample output that I might want to use to ingest into a downstream kind of system. So if I'm an end user and I'm trying to understand, okay, how is this smaller model working? I can come in and look at loss curves, and I can see that indeed, okay, look over here, my validation, my model is converging. It's going from a loss of 10 down to 5 after just a few hundred micro batches. That's good. That's good news. It means it's working. I can validate also very quickly that my validation error and validation loss in this case is slightly worse than my training loss, which is exactly what we would expect for a model that's actually performing. So that's exciting. It's very easy to kind of see this and start to make progress. So I talked about starting small, again, small job that in this case runs on 16 GPUs instead of a few thousand, and scaling up. We can, again, change this one parameter from one kind of set of one slot to 16 slots. I could keep increasing this up to hundreds or thousands as we have with many customers, and you could expect it to scale pretty well. But there's a catch there, and that is that with this type of 3D parallelism that we've talked about here, We have these three kind of crucial parameters here: the micro batch size, the pipeline parallelism, degree of model parallelism. These are factors that control the degree of parallelism that is going on under the scenes. And these, changing these numbers results in very different communication patterns between nodes in the distributed system. And what we found empirically is that bad settings of these models or of these parameters can indeed lead to a real poor throughput. And so how do you solve this problem? You could sit down and think really hard about how data is being transferred over the network, and the balance of compute to data transfer, and what is the setup that is going to maximize kind of total throughput of the system. That's one option. And we've got customers who have tried that. But instead, what we proposed when we were working with a customer on this very problem was, let's not go and let's not write down a fancy theoretical model. Let's actually test empirically what works. And so what we proposed was a very simple and elegant change to this file, the configuration file that you're looking at right now, that says, instead of running a bunch of experiments or what have you on independently trying to figure this out, let's turn this into a hyperparameter optimization problem. And so I've switched tabs here now, and what you see is the main change that we made to this file was to move from a fixed set of values for these configuration parameters that I showed you before to a search space. And we're turning this into a hyperparameter search problem, but it's a unique one in that instead of targeting accuracy or something like that, what we're targeting is teraflops, that is total throughput of the cluster. You could think of this as images per second or examples per second in this case for text. But instead of maximizing for accuracy, what we're maximizing for is throughput. And so we submit this job to the determined cluster, and it creates, so first off, we're not running all of these jobs all the way to convergence. What we find is after a few hundred batches, these jobs converge on pretty consistent teraflops. So that is, the total throughput stays constant over the life of the job, which means you can run a small percentage of that long job, many of them, and get a good sense for what the shape of that overall throughput looks like. And so I'll come back to my dashboard here, and I'll show you the results of this hyperparameter optimization on this particular code base. So the thing that I want to draw your attention here is the y-axis. So on the left, you've got best performing job in this batch as 37 teraflops of total throughput. Meanwhile, the worst performing job is about 20 teraflops. Again, this is a small demo cluster, just 16 or so GPUs at once, older model GPUs, so not really representative of what we'd expect to see on an A100 and with proper networking. Again, this is over Ethernet, not on InfiniBand, but it gives you a sense of what the potential impact is here. And so on this particular cluster, what we found was that by varying these parameters that lead to the types of 3D parallelism that we talked about, we can have our worst job run at 20 teraflops and our best job run at nearly 40. And so that's nearly a 2x increase in throughput between a bad job and a good job. And that translates directly to dollar savings, right? So it could mean taking that $3 million job and cutting it in half almost. That's pretty phenomenal. And that happened over the course of a quick run of this run with determined AI. Now, what are the odds that you're going to pick the absolute worst configuration here? Pretty slim. So caveat emptor, I think that 50% job savings isn't necessarily realistic, but even versus an average job in this mix, we end up saving significant 10-20% pretty easily. Now, the other thing that determined lets you do is begin to explore, okay, what are some of the reasons why my job was performing better or worse? And I can start to dig into, say, parallel coordinate plots that help me understand, okay, this high degree of data parallel world size does seem to be correlated with better performing throughput. Again, we can look at this. The other thing I guess I'll show just briefly here is, as I'm trying to dial in on my job performance, I can also begin to look at the characteristics of the job itself. And I can begin to ask questions like, okay, how was my overall GPU utilization of this particular job? And I can see in this job, okay, pretty good. I had nearly 100% GPU utilization across every GPU in the cluster. I can also see how many samples I was processing over time. And Determine can let you kind of look in detail about individual job performance as well as overall cluster performance. And so, the key takeaway here is that, again, this is an example of how tooling that helps you reason and automatically work at scale can help save a ton of time and a ton of cost, and really accelerate sort of the time to insight and the time to produce these really high quality applications that are driving success in the industry. So really appreciate you all taking the time this morning. We're over by a minute. Looking forward to attending future sessions, and thank you for having me as part of the HPE Dev community.